Hello, welcome to our lesson on antiderivatives. So an antiderivative is exactly how it sounds. It is the opposite or the inverse of a derivative. So it is the inverse, again, or opposite of what we've been working on for this entire course. The opposite of a derivative, the inverse of a derivative. Okay, so when you're working on antidifferentiation, that is the process of finding an antiderivative, what you're trying to do is determine the original function given its derivative. So instead of here's a function, find the derivative, it's here's the derivative, find the original function. So the antidifferentiation is what we call the process of finding the antiderivative. And again, what you're trying to do is figure out what is the original function because you are given its derivative. So you're working backwards. Similar to when probably remember early in algebra, you multiply out two binomials and you end up with this trinomial, and the process of multiplying is pretty simple. Like derivatives have, gotten to be pretty fluid for us because we've practiced a bunch. Now working backwards would be like, okay, take this trinomial and try to factor it. At first it's a little tough, but once you get the hang of it and you've worked on it long enough, then it's not so bad. So that's going to be similar here. At first it's going to feel a little weird because we're working backwards, but the more you practice it, the more fluid and fluent you will become. Now, antidifferentiation is also known as integration. So we can say finding or the process of antidifferentiation is the same as the process of integration, and when we're finding an antiderivative in that antidifferentiation process, again, we can call it integration as the process or an integral as the result of the process. So antidifferentiation or integration and antiderivative or integral. And there are a couple different types of integrals. There's what we call an indefinite integral, there's a definite integral, and I'll explain one of those in today's lesson. So I just want to help you wrap your brain around the concept, again working backwards from differentiation. So for instance, if I said to find the derivative with respect to x of 3x squared, we know to use our power rule, so we multiply by our exponent and then subtract 1 from that exponent, so it would be 3x squared. So instead of take the derivative and end up here, now we're going to be given the derivative and we're asked to figure out what was the original function that produced that derivative. So this is the symbol that's going to tell us to do that. This is our integral symbol. It says find the integral. It says find the antiderivative, figure out the original function that produced that 3x squared. Now this dx that's here just tells us that this derivative was taken with respect to x. We call that the differential. So it doesn't really affect the work of the process. So we have 3x squared here. We know that that derivative came from x cubed. So we would say that the antiderivative of 3x squared dx would be equal to x cubed, with one small exception. When we take the derivative of x cubed, we get 3x squared. But if I was to take the derivative of, let's say, x cubed plus 1, that derivative with respect to x would also be 3x cubed, because the derivative of the constant would be 0. Or if that was an x to the third plus 7, then our derivative would still be 3x squared. Or if it was an x cubed minus 4, then our derivative would still be a 3x squared. So the idea is when we're working backwards, we should be able to take the derivative of this and land here. Now we can absolutely take the derivative of x cubed and get to 3x squared, but there's no guarantee that there wasn't a constant of some sort on that function. So because there could be a constant here that zeroes out when we take its derivative, we have to account for that when we integrate, when we antidifferentiate. So we're going to say it's x cubed plus some constant that we're going to call c. Now again, if I was to take the derivative of x cubed plus a constant with respect to x, we're still going to end up with 3x squared, and the derivative of the constant is 0, so we still end up here where we need to be. Okay, so this is why we are going to refer to this as an indefinite integral, because it isn't definitely one particular function. It's what we call a family of functions. So x cubed plus any constant could be in that family. So this would be part of the family, right? So we're going to call this, again, an indefinite integral, and this is going to be a family of integrals or a family of antiderivatives. And I don't know why I dashed that. Antiderivatives. Okay, and that constant, basically every time we anti-differentiate or we integrate, we're going to put that constant there, that constant c, because we don't really know if it belonged there in the first place. Even if it doesn't belong there, if it was a 0 for c, then we would be fine. So that accounts for any possible constant that could have been with our function, and we differentiated and it just went away. Okay, so that is the concept. Now I just want to talk about a little bit more notation so that we're comfortable, and then we'll look at some of our rules. So capital F of x is notation for our antiderivative of f of x, and so that if we took the derivative of that antiderivative, we would get back to the function that we were looking at, similar to what we just saw. But my bigger focus would be on this here. So this is our notation. This, we just saw, is called the integral symbol. So this is our integral. Where do I want to put my arrow? Make this look nice. Let's call this the integral symbol. It is what is telling us to integrate or to anti-differentiate, just like this tells us to differentiate with respect to x. Okay, if I didn't say find the antiderivative in words, that's the symbol that's telling you to do it. And this part here we're going to refer to as the integrand or integrand. I like integrand better. And then this part here, this dx, again, that's just telling us that we differentiated that function. That derivative was taken with respect to x. So we're going to call that the differential. Differential. Okay, and then this whole thing over here is our antiderivative. So this is our antiderivative. Technically, it's a family of them. So that's our antiderivative, or that's the result of our integration. And then C all by itself here. I need another color. Okay, this is not my favorite color, but we're going to go with it. This is called the constant of integration. Yeah, that's terrible. I don't even know why that's there in a preset. Let's try orange. Yep. Okay, so that's our constant of integration. And that's probably the most common mistake I see in integration, is people forgetting to put the constant of integration there. It doesn't make your work wrong, but we have to account for that constant of integration. So it needs to be there. That'd be like a, partial point taken off if you forgot it. Okay, so that's the concept. Instead of find a derivative or take a derivative of a function, it's here's the derivative, find the original function. So working backwards from what we've been doing. So when I introduce these integration rules, what I'm going to do is show you the derivative first. That way we can make some connections, and then we'll do a few examples and hopefully we'll be okay. Again, the more practice, the better it will be and the easier it will get for you. So for instance, here, if we're taking the derivative with respect to x of k just represents some constant, okay, multiplied by x to the first. Well, we know if we were taking the derivative of, let's say, 3x, that would just be 3. Technically, you could use your power, right? Multiply here, you get your 3, but then you would subtract 1 from the exponent, and that would leave you x to the 0, and x to the 0 would just be a 1. So we know that the derivative of 3x would just be 3. So all we're saying here is if we take the derivative of something that is linear, right, that linear term there is going to go away. We're going to be left with the constant that is in front of the coefficient of that linear term, so like the slope, right? So the derivative of a linear function is the slope. That should make sense. So if I'm taking the derivative of something linear and ending up with a constant slope, then when I take the integral of a constant, I should get something linear, because we're working backwards here, and that's all this rule is saying. When I take the integral, if I anti-differentiate a constant, remember this is just saying we differentiated with respect to x, then I'm going to end up with something linear. So it's going to be that same constant multiplied by x to the first, again, plus our constant of integration, so plus c every single time. So for instance here, we're looking for a function given that its derivative is 4. So if its derivative is 4, that function had to be 4x. So if I took the derivative of 4x, that would take me back to 4. And then we're going to say 4x plus c, because the derivative of 4x plus c would also be 4x. Okay? If it was the integral of negative 2 dt, that means we differentiated with respect to t this time. So instead of negative 2 times x, this would be negative 2 times t plus c. Again, if I took the derivative, if you weren't sure if you did it right, just take the derivative with respect to t this time of whatever you're saying the integrand or the antiderivative should be, so negative 2t plus c, and does it get you back to what you have here? Well, the derivative of negative 2t would just be negative 2, the derivative of the constant 0, so in fact we do. Okay, so that's kind of the nice thing here. You can always check your work by just differentiating your result, and it should take you back to the function you're integrating. Okay, so that's our constant rule for taking the integral or anti-differentiating a constant. We get something linear. Then we have our power rule. So working in reverse, again, it's a little strange. We know our power rule, so if I was differentiating, when we just did this a second ago, like x to the third power, that we multiply and then we subtract 1, right? So multiply by the exponent, subtract 1 from the exponent. So we need to do those opposite operations. Instead of subtracting 1 from the exponent, we're going to add 1 to the exponent, and instead of multiplying the exponent, we're going to divide. And we want to do those in reverse. So instead of multiply and then subtract, we're going to add and then divide by the thing the exponent that was added to. So if we're integrating, anti-differentiating, finding an antiderivative of x to the nth power, it will be a fraction of x to the n plus 1 power divided by n plus 1, and again, we're going to add that constant of integration. So for example, the integral of x to the 5th, the antiderivative here, so we're going to add 1 to the exponent, making it x to the 6th, and then divide by that exponent that was increased by 1, the new exponent. So we're going to divide by 6 here, and then we're going to add on our constant, and that's it. So if you wanted to rewrite this, you could. I don't necessarily like that fraction form, but you could totally leave it there. I'm just going to call it 1/6 x to the 6th plus c, but either one of those answers would be fine. And again, if you're not sure if you did it right, think about taking the derivative here. If you took the derivative, you would get 6 times the 6 is 1, x to the 6 minus 1 would be 5, and the constant would go away, and that's exactly what we have here. Okay, so you can always take the derivative if you're not sure if you did it right. So then here, this is y to the negative 4th dy, so this was differentiated with respect to y. So we're going to take our y, and then we're going to add 1 to the exponent, so negative 4 plus 1 would be negative 3, and then divide by that new exponent, negative 3, and then add on our constant. Or again, if you wanted to, this one actually we should clean up, we don't want to leave that negative exponent there. So I would make this 1 over negative 3 y to the positive third. So in this one, I have the x after the fraction because it technically belongs to the top, but this one, the y needs to be in the bottom of the fraction, and then plus c. Or here, same thing. Okay, we have x to a power, so we're going to add 1 to the power, so x to the 2/3 plus 1, which is 3/3, would be 5/3. And then we're going to divide by that new power, so divide by 5/3, and then add on our constant. And we're definitely not going to leave a fraction in a fraction, but dividing by 5/3 is the same as multiplying by its reciprocal 3/5. So a better answer would be 3/5 x to the 5/3 plus c. Okay? Alright, so there's our power, our power rule in reverse. Another rule we've talked about is if we have some function being multiplied by a constant, then we can take the derivative of that function and multiply by the constant. So the constant can just sort of sit there, just hang out, bring it back in after you differentiate. So for example, if it was 3 times x squared, I could just use my power rule and call this 6x, or I could do 3 times my derivative of x squared would be 2x to the first, and I would get that same 6x, right? So I can differentiate my function and then just multiply by my constant. The same is going to be true for integration. If we are integrating and we have a constant times a function, that's what this is saying here, then we can just integrate that function and then multiply by the constant. All right, so for example, here, if I was integrating 4x cubed, that would be the same as 4 times the integral of x cubed. Because x cubed I can integrate, so this is going to be 4 times x cubed becomes x to the add 1 to the exponent, divide by the new exponent, and then add our constant of integration. And then we can simplify the times 4, divide 4, those are going to cancel there, and so we're going to be left with x to the 4th plus c. And then I just like to check my work sometimes, especially when I first start to do this. If I took this derivative, took the derivative here, I would have 4x cubed, which is exactly what I have, so I'm verified. I'm good. Okay, so same thing here. I have y to the 5th being multiplied by that 3/4, so I'm just going to take that out. This is the same as 3/4 times the integral of y to the 5th dy, and so this will be 3/4 times the antiderivative for y to the 5th is going to be y to the 6th divided by 6. So add 1 to the exponent, divide by that new exponent, and then a plus c. And again, this one can be simplified a little. We can reduce here. 3 goes in there once and in there twice. So our coefficient is going to become 1/8. So we have 1/8 y to the 6th plus c. All right. And I don't know why I had so much space for that. Okay, so next rule, flip the page, here we go. The next rule, again, we applied to derivatives. We said if we were differentiating a sum or difference of multiple functions, like if it was 3x squared plus 2x minus 7, if I was taking the derivative with respect to x of all three of these terms, I just differentiate them separately. So take the derivative, take the derivative, take the derivative, right? It's the derivative of a sum or difference is the sum or difference of the derivatives. Same for integration. So if I'm taking an integral and I have multiple terms there, I can integrate them separately, okay? So again, the integral of a sum or difference is the sum or difference of the individual integrals. So for example here, if I was integrating 5 minus x, that would be the same as the integral of 5 minus the integral of x. And if you forgot to write the dx there, it's not going to affect your work, but if we're being precise, then we should have that there. So the next step is to, again, take our individual integrals. If I'm integrating a constant, that's going to be a linear function, so the integral of 5 would be 5x minus the integral of x to the first is going to be x to the second divided by 2, so add 1 to the exponent and divide by that new exponent, and then let's put our constant of integration there. You don't need to put that constant of integration twice, just once is good, because technically it was one function to begin with. All right, and you can leave that answer there. I just prefer the fraction, the coefficient as a, the fraction to be a coefficient and not the whole, I don't know what I'm saying. I don't like this version of that, so I'm going to make this 5x minus 1/2 x squared plus c. Okay, yeah, that's what I was trying to say. Let's try another one. So here, again, I'm going to split this up, and I'm actually going to do some rewriting here as well. So I'm going to take the integral of the square root of x, I know is x to the 1/2. If I have it as a power, I know what to do with that. Dx plus, this is going to be the integral of, I'm going to make this 1/2 and then x to the negative 1/2. So that's x to the 1/2 on the bottom, so that's going to become 1/2, and actually I can bring that 1/2 out in front. So 1/2 as a constant multiple, and then this would be x to the negative 1/2, and then our dx. Okay, so I just rewrote this as x to the 1/2. I factored out this. It's like factoring out that 1/2 there, that constant, move that out. And this is on the bottom of the fraction, so it's x to the negative 1/2. So hopefully I didn't lose you there. And now we're actually going to integrate. So x to the 1/2 becomes x to the add 1 to the exponent. So 1/2 plus 1 would be 1/2 plus 2 over 2, which would be 3 over 2. And divide by that new exponent, 3 over 2. Plus this is going to be 1/2 times x to the negative 1/2 plus 1, again 2 over 2 becomes a positive 1/2, and divide by that new exponent, and then add on our constant. And now we're just going to clean these up because these complex fractions look terrible. So again, dividing by 3/2 is the same as multiplying by 2/3, so I'm going to call this 2/3 x to the 3/2, plus over here I have a times 1/2 and then a divide by 1/2, which is multiplied by 2. Those two are going to cancel, so I'm just going to be left with this x to the 1/2. And then I have my plus c. And that would be a perfectly acceptable answer. Although, because this started with radicals, it might be better to put it in radical form. It's just, if this was in your homework, I'm going to have the rational exponents because I don't know how to make you type in those radicals. So I'm going to say this one, or we can call this 2/3 times the square root of x cubed plus the square root of x plus c. So either one of those perfectly fine. I'm totally good with this. But just if it starts with radicals, sometimes nice to end the way that it begins. Although, again, either one. All right, so let's try one more here. We're going to piece this out. Now, we haven't talked necessarily about a quotient of polynomials, but we don't have to leave this as a quotient of polynomials. I can actually divide this. So that would be my first step here, is to make this, to actually divide each of these terms by t squared. So t squared divided by t squared would just be 1. And then 2 divided by t squared, obviously that doesn't divide, but I would rewrite that as 2t to the negative second. And so this now is what I'm going to try to integrate. And again, I can separate this out. So I can make this the integral of 1 dt plus the integral of 2t to the negative 2 dt, and now integrate each one of these separately. So the integral of a constant is going to be linear, so it's going to be 1t plus over here, actually I could have written this out here. Let me just move that. So I'm going to factor out that 2. So it's twice the integral of t to the negative 2. So this will be 2 times t to the, add 1 to the exponent, making it a negative 1, divide by the new exponent, negative 1, and then add our constant of integration. So we're good there, or just clean it up. I would call this t, and then that's going to become a negative 2 here for our coefficient, and t should really go to the bottom of the fraction. So this is going to be a minus 2 over t, and then a plus c. And that would be a good spot to stop on that one. Okay, so a couple more rules, and I think we'll be good. Although there are a ton more integration rules, the ones we're going to look at today are going to suffice. They're going to meet the needs of what we need to do. Luckily, we don't have to get into trig and some of the other exponential and log things. So let's talk about e to the x. Remember, e to the x is an easy one because the derivative of e to the x is itself, e to the x, which means the integral of e to the x will just be e to the x. The only thing is we got to remember our constant of integration. So here, it's being multiplied by 3, no big deal. 3 times the integral of e to the x is just going to be 3 times e to the x plus c. Okay, so if the derivative of e to the x is e to the x, then the integral of e to the x is e to the x. If it's being multiplied by 3, then multiply by 3. All right, that was easy, piece of cake. All right, last one we're going to talk about is the natural log and 1 over x, that connection there. So when we're taking the derivative of the natural log, we said the derivative of natural log of x would be 1 over x. Now remember, we talked about the absolute values being proper notation there, because whether x is positive or negative, we ended up with the same derivative. So here, if I'm taking the derivative of the natural log and I get 1 over x, that means when I take the integral of 1 over x, I get the natural log of x. And we want to make sure to keep the absolute value there. Not only is it proper, but we can't evaluate logs of negative numbers. So another reason we want to have that in there. Just don't forget your plus c, okay? And actually, this is one where we want to be particularly careful. Let me just point something out real quick here, and you don't need to write this if you're taking notes, but maybe you do, I don't know. If I saw 1 over x, I would be tempted to write that as x to the negative first, okay? So let's pretend, and this is why I don't want you to write it because it's not right. Let's pretend I wanted to integrate in that form, x to the negative first. If I applied my power rule, then I would add 1 to my exponent, which would make it x to the 0, and then I would divide by that new exponent would be 0. And so I run into some problems here. Well, x to the 0, or anything to the 0 is 1, so this eliminates x, but also we end up with division by 0, which is not defined. So you can try to apply your power rule, but it's not going to work here. So we need another rule, which is the one we have, and it connects directly to our differentiation. So you might be tempted to differentiate x to the negative first, but we can't. We want to use our natural log rule here for integration. So on this one, this does not look like 1 over x yet, but this can be reduced. So if I reduce out the common factor of x, then I have 2 over x dx. And this is close to 1 over x, but it's being multiplied by 2. So this is really the same as 2 times 1 over x dx, and there it is. So it's 2 times the natural log of x plus c, and x in absolute values to be proper. Okay, kind of similar on this one. I don't want to integrate all this mess, so I'm going to, this mess of a fraction anyway, I'm going to go ahead and divide all 3 of the terms in the numerator by the x squared. So if I divide, I end up rewriting my integral as, well, 3x squared divided by x squared would be 3, plus 5x doesn't divide by x squared, but just like this situation here, I can reduce a factor of x, so that would go and that would go, and that would leave me 5 over x. So plus 5 over x, and then, not plus, but minus, 1 doesn't divide by x squared either. So I can leave that way, and then this is all technically being has been differentiated with respect to x. So now I'm going to apply a few of my rules here, okay? I'm going to separate this out, make this 3 separate integrals. So it'll be the integral of 3 plus, this is 5 times the integral of 1 over x minus, almost did a plus again, the integral of, I'm going to rewrite that 1 over x squared as x to the negative second. And now that I have these 3 separate integrals, I can integrate. So the integral or antiderivative of a constant is going to be linear, so this is going to give me a 3x. Plus here it's 5 times 1 over x. Remember, that's our natural log of x. And then here we're going to subtract. This becomes x to the, add 1 to the exponent, and then divide by the new exponent. And then finally, we'll add on our constant of integration. And again, you could leave it like this. I probably wouldn't, so I'm going to go one more step. 3x plus 5 times the natural log of x. And then the negative here is going to cancel and make a positive. And then x to the negative first is really 1 over x. And that would be best form of the answer. Okay? So put in a bunch of different rules into that one problem, but it's good practice. Now, each of these integrals, again, we call indefinite integrals because we have a family of antiderivatives here. It's not a definite, like for sure, this is what the function is. This is a possibility, right? Because c can really be any real number. So if I wanted to find an actual function where I figured out the value for c, find a particular antiderivative by finding that value of c, we need a little bit more information. So let's look at a few more examples where we find a particular antiderivative. So we actually get the function with the value of c in it. For instance here. So first it says find f of x given its derivative. That's what we're doing with integration. And then it says f of 10 equals negative 10, and that's how we're going to find the value for c. So let's first integrate this. We're looking for our original function given its derivative. So let's go ahead and find the integral for 1/5 x minus 2, and obviously this was differentiated with respect to x. So I'm going to rewrite this as 1/5 times the integral of x, and then minus the integral of 2. Oops, I forgot my dx here. It's not going to affect your work, just want to be proper. Integral of 2, and so we end up with 1/5 times x to the, add 1 to the exponent, divide by the new exponent, minus the integral of the constant. Antiderivative of the constant is going to be linear, so that's 2x, and then plus c. So this was our derivative. That means this is our function, okay? Now I just want to clean that up a little bit. So I'm saying we found the original function by integrating the derivative, finding the antiderivative. It becomes 1/10 x squared minus 2x plus c. Now that's a family of functions technically, because I could plop whatever I want in there for c, but in this case we know a particular point on the function, so we can actually find the actual function for this situation. If f of 10 is equal to -10, that means when I input 10 for x, my output should be a -10. So I'm going to do that. I'm looking at 1/10 times an input of 10 squared minus 2 times an input of 10 plus some constant that I have to try to find. The result of that, according to that piece of information here, that coordinate, all of that should end up being -10. So now I have an equation that I can solve to actually find the value for c. So 10 squared is 100, and a tenth of that's going to be 10. So this is a 10 here. -2 times 10 makes a -20. And 10 minus 20 is -10, which means c has to be 0 in this case. So c is 0, then now I know the exact particular equation, the exact particular function for this situation. So I can say not a family of functions, but f of x is exactly, not negative, but 1/10 x squared minus 2x without having to put a plus c there. So that's the particular function, the particular antiderivative that we're looking at here. Okay? So we're going to try this again, but this time we are not given the first derivative, we're given the second derivative. That's okay. If I integrate the second derivative, I can find the first derivative, and if I integrate the first derivative, I can get to my original function. So that's what I'm going to do. I'm going to start by integrating x squared, and that's going to give me the first derivative. So if I take the antiderivative of the second derivative, I get the first derivative. Alright, so it just backs me up one step here. So this is going to be x to the third divided by 3 plus c. Now again, I need to be specific here, and this is technically my first derivative now. So it's x cubed, let's rewrite this, 1/3 x cubed plus c. But right here it says that my first derivative at 0 is going to be 6. So I'm going to input a 0 for x. So I'm looking at 1/3 times an input of 0 cubed plus some value of c, and all of that should end up making an output of 6. So I'm going to put that in here for my output. Now, 1/3 times 0 cubed is just going to be 0, so that means that c has to be equal to 6. So now I know my first derivative is not a family of functions anymore. It's definitely going to be 1/3 x cubed plus 6. Okay? So there's my first derivative. Now if I take the antiderivative of the first derivative, I'll get to my original function. So now I'm going to integrate 1/3 x cubed plus 6. And I'm going to separate this out. So this will be 1/3 times, or so 1/3 times the integral of x cubed plus the integral of 6, and I end up with 1/3 times x to the add 1, divide by the new exponent, plus the integral of that constant's going to be linear, and then my constant of integration. So this is my original function now, right? I've got f of x equal to 1/12 x to the 4th plus 6x plus some constant. And if I didn't have this last bit of information, I would be stuck there with that family of functions, but because I know f of 0 is equal to 3, I can input 0, make an output of 3, and actually solve for c. So I'm going to do that here. I'm going to say, excuse me, 1/12 times an input of 0 to the 4th, plus 6 times, again, input of 0, plus the constant that I'm looking for. All of that should amount to my output, which is 3. Those zeros make those terms cancel. That means that c has to be equal to 3. So c is equal to 3, and now I have the particular function I was looking for. So I'm going to say, finally, that, not enough colors, our function is precisely 1/12 x to the 4th plus 6x plus not just any old constant, but 3. So that is our function. And remember, if you weren't sure if you did all that right, take the derivative of that function, see if you get here, and then take the second derivative, take the derivative of the derivative, and see if you get here to x squared. So you can always work backward and verify what you've done. I don't know why I deleted that, and there you go. Okay? So hopefully you're good and you got enough to get going on your assignment, but as always, if you have questions, need some extra help, then reach out. Until next time, take care.